Hey you guys, this is Mr. Millings, and in this video we are going to learn how to take measurements of length, mass, volume, and temperature. So let's first take a look at how we are going to measure length. When we're measuring length, it says right here that when we take a measurement from a scaled instrument, meaning not a digital instrument like a meter stick here for example, you must record the measurement one significant figure beyond the level of precision of the instrument that you use to take the measurement. So what the heck does that mean? Well, if we take a look here, we have a meter stick or a section of a meter stick, and if we take a look close, the distance between 0 and 1 here, if we take a look, is 1 centimeter, right? And so if we take a look even closer, we can see that this meter stick here is precise to the 10th of a centimeter, right? It's precise to the 10th of a centimeter. So when we take a measurement using this meter stick here, for example, if we wanted to take a measurement of the length of this pencil here, we are going to have to do so one significant figure beyond the level of precision of our meter stick here. Our meter stick is precise to the 10th place. Therefore, when we take a measurement of the length of this pencil here using this meter stick right here, we have to go one beyond the 10th place, one significant figure beyond the 10th place in our measurement, or to the 100th place. So our final measurement of this pencil here using this meter stick that is precise to the 10th place, or the 10th of a centimeter, is going to have to be to the 100th place. So if we take a look, we know with 100% certainty that this pencil is at least 6 centimeters. It's not quite 7. We know that it is at least 6 centimeters, right? So we'll go ahead and put a 6 right here. Furthermore, if we take a closer look, we can see it's 6.1, 6.2, 6.3, 6.4, 6.5, but it's not quite 6.6. So we know with 100% certainty that this pencil is 6.5 centimeters in length. But now what we have to do, because our meter stick here is precise to the 10th place, we have to go one significant figure beyond that. We have to estimate what the 100th place is going to be. So if this is 6.1, 2, 3, 4, 5, we can see that this red dashed line here is not quite to the 6.6 line here, and it's a little bit shy of that, right? So it's a little bit more than halfway. So we might say that this is 6.56 or 6.57 centimeters. So we'll call this 6.57 centimeters. So the length of this pencil is 6.57 centimeters, but understand that concept that when we take a measurement of length, we have to measure this pencil or whatever object that we are measuring one significant figure past the level of precision, right? So we had to estimate the 100th place here, whereas these two figures or digits in our measurement are certain, right? These two are certain. These are the certain significant figures in our measurement based on the precision of our meter stick here, and we had to estimate the 100th place. So let's apply this concept to several different examples. In this example, it says we have to determine the length of the pencil. So if we take a look at this pencil here, we can see that this pencil with 100% certainty is at least 6 centimeters. In length, it's not quite 7. So we know it's at least 6 centimeters in length. And if we take a closer look here, we can see it's 6.1, 2, 3, 4, 5, 6, 7, 8. It's not quite 6.9 centimeters in length. With 100% certainty, we know it's 6.8 centimeters in length, and now we have to estimate one significant figure past the level of precision of our instrument. So if we take a look at this red dashed line here, it appears to be a little bit more than halfway in between 0.8 and 0.9, so we'll call this 6.87 centimeters. So the length of this pencil is 6.87 centimeters. Let's take a look at another example. If we take a look at this pencil right here and we want to determine its length, we know with 100% certainty that the pencil is at least 8 centimeters. We also know if we take a look that it's at least 8.1, 2, 3, 4, 5, 6, 7, 8, 9 centimeters, 8.9 centimeters in length. And our last significant figure here, we are going to have to estimate. If we take a look here, it's pretty much, or it's very close or approaching the 9 here. So we'll take a look close and we'll probably estimate this to be at 8.98 centimeters in length. Let's take a look at this one. If we wanted to figure out the length of this pencil, we can see with 100% certainty it's at least 3 centimeters in length. And if we take a look, it's 3.1, 2, 3, 4, 5, 6, 7, not quite 3.8, so it's 3.7. And this dashed line is very close to the 3.8 line, so we'll call that 3.79 centimeters. Let's take a look at another one. Let's take a look at the length of this pencil. If we take a look at the length of this pencil here, we see with 100% certainty that this pencil is at least 7 centimeters in length. It's 7.1, 2, 3, 4, 5, 6, 7, 8, so it's not quite 7.9, so it's 7.8. And if we take a closer look and estimate the hundredths place, or the second decimal place here, we'll call that 7.87 centimeters. Let's take a look at this last example of length. If we take a look at this pencil here, we can see that the pencil here is at least 5 centimeters in length, and you guessed it, it's 5.9 centimeters with 100% certainty. And now we have to estimate what this hundredths place is going to be, and it looks to be just a little bit shy of halfway in between this point here and this point here, so we'll call that 5.94 centimeters. So keep that in mind, that when we take measurements of length, we have to measure one significant figure beyond the level of precision of the instrument that we are using. Let's now switch gears and see how we're going to measure mass next. And so when we measure mass, we can use an electronic balance or we can use a triple beam balance. And a lot of high school chemistry labs still use the triple beam balance. So it says right here that when taking a measurement from a scaled instrument, such as a triple beam balance, not a digital balance or electronic scale, you must record the measurement one significant figure beyond the level of precision of the instrument you use to take the measurement. So if we take a look at the example of the triple beam balance below here, we can take a look and see that this triple beam balance, first of all, is measuring in grams, right? We can see grams labeled right here. And so we know that this scale is measured using the unit grams. So we have our grams right here. Furthermore, if we take a look, we can see that this scale is precise to the tenth of a gram. From 0 to 1 here, this distance represents 1 gram. And so all these tiny little lines here, they're going to represent 0.1 grams. So 0.1 grams, 0.2 grams, all the way to 1 gram. So this triple beam balance here is precise to the tenths place. And so when we take a measurement of an object that is placed on here, we have to go one significant figure past the tenths place. So we're going to have to measure this object to the hundredths place, or 2 decimal places. And so what's the mass of the metal that is placed on this scale going to be? Well, we have 300 right here. This little marker here is set at 300. We have 30 right here. So 330 we know with 100% accuracy. And let's take a look. And precision, accuracy and precision. And if we take a look right here, we have 338, right? 338. And if we take a closer look, it looks like it's 338.1. And now we have to estimate the hundredths place, right? We have to take a look really closely and see that this is about 338.12. It's just a little bit past the 0.1 line. So the mass of this metal here is 338.12 grams. So that's how we're going to use the triple beam balance to measure the mass of different substances. Let's take a look at another example. So in this example, we have some sort of chemical that has been placed on the triple beam balance, and we have to determine the mass. So we know that it's 200 grams with 100% certainty. So 200, we have 70 right here, 270 plus 4, right? It's not, I'm sorry, plus this right here is past 4, not quite to 5, so it's 274 grams with 100% certainty, and it's 204.123 4, 5, 6, not quite the 7. And if we take a look, this appears to be pretty close to the 0.7 line, so we'll call this 274.68 grams. So the mass of the chemical substance that's on this triple beam balance here is 274.68 grams. Let's take a look at another one. So it looks like we have a gold bar that's been placed on this triple beam balance, and we see that first of all, with 100% certainty, it's 500 grams plus 40 here. So 540 plus 7. This little slider here is beyond the 7, not quite to the 8. So 547 grams with 100% certainty. 547.1, 547.2, 547.3, 547.4, and it's a little bit past the 0.4, so we'll call this a 1. 547.1 grams is going to be the mass of this object here. Let's take a look at another one. In this example, we have to determine the mass of this ring right here. And so if we take a look, the little marker here is set at 0. So we have 40 right here. So 40 plus 2, it looks like. This little slider here is beyond the 2, not quite to the 3, so we'll have 42. And if we take a look, this isn't quite to the 0.1 line, is it? So we'll have 42.0, and we'll go ahead and call this 0.08. We have to estimate this right here. 42.08 grams is going to be the mass of this this ring that's been placed on this scale. Let's take a look at one more example. In this last example, we need to determine the mass of these silver coins that have been placed on this triple beam balance. So let's take a look. If we take a look here, we have 500 grams plus 80 grams, so 580 plus the 4 right here. This slider is beyond the 4, not quite to the 5, so we have 584 grams. And if we take a really close look, we can see that this slider is beyond the 0.1, so not quite the 0.2, so 584.1, and now we have to estimate where this is right here, and we'll go ahead and call this 584.12 grams. So that is how we're going to take measurements of mass. Let's now learn how we're going to take measurements of volume. So let's now take a look at how we're going to measure volume. It says right here that when measuring volume from a graduated cylinder, you must record the measurement one significant figure beyond the level of precision of the instrument that you use to take the measurement. So in the examples below, we have several different graduated cylinders here, and when we come across a graduated cylinder that we're going to use to measure the volume of different liquids, what we first have to do is we have to figure out how the graduated cylinder is graduated. In other words, by what increments these different cylinders are graduated by. And if we take a look at this first graduated cylinder here, we can see that each one of these little lines here represents 1 milliliter. If this is 10 milliliters here, and this is 20 milliliters here, then each one of these little lines represents 1 milliliter. So the graduated cylinder here is graduated by increments of 1 milliliter. And if we want to take a reading from this graduated cylinder right here, we need to measure one significant figure beyond the level of precision of our graduated cylinder, which is 1 milliliter. It's graduated by 1 milliliter increments. So when we take a measurement, we have to go one significant figure beyond the ones place. So our final measurement should include only one decimal place here. This would be 70.0 milliliters, not just 70 milliliters. If we take a look at this graduated cylinder right here, if we take a close look, we can see that the graduated cylinder here is graduated by increments of 0.1. If this is 1 milliliter, this is 1.1, 1.2, 1.3, 1.4, 5, 6, 7, 8, 9, and up to 2 here. So each increment here on this graduated cylinder is 0.1 milliliters. And anytime we have a graduated cylinder that is graduated by increments of 0.1 milliliters or by 0.2 milliliters like we see in this graduated cylinder here, then our final measurement needs to be taken to the hundredths place, or one significant figure beyond the tenths place. So if we take a reading from here and we just put 5.2 milliliters as our final measurement, this would be incorrect. We need to carry it one significant figure beyond that, right? We have to estimate what that's going to be. And same thing right here. If the increments that this graduated cylinder is graduated by is 0.2 milliliters, then what we will need to do is we will need to estimate the hundredths place. We need to take our measurement one significant figure beyond the level of precision of our graduated cylinder. So if we just simply said that the measurement of the liquid in here is 13.2 milliliters, this would be incorrect. We would have to carry it to the hundredths place. We'll have to estimate this final spot right here. And if we take a look at this graduated cylinder right here, the graduated cylinder right here is graduated by increments of 0.5. And when we have a graduated cylinder that's graduated by 0.5, it gets a little tricky and it kind of violates the rule that we just talked about. If you have a graduated cylinder that is graduated by 0.5 milliliter increments, in this instance here we are simply going to measure the liquid that's in the graduated cylinder to the tenths place, okay? So we can't have 27.30 milliliters here, because what ends up happening is we're going to have to estimate this significant figure and this significant figure, and we can't estimate two significant figures in a measurement. We can only estimate one significant figure beyond the level of precision. Alright, so keep that little rule in mind, but understand how that works. And now let's go ahead and take a look at how we're going to measure volume and apply this concept to several different examples. And so before we can start taking measurements of volume using a graduated cylinder, what we have to do is first take a look at what happens when we put water in a graduated cylinder. When we put water in a graduated cylinder, an interesting phenomenon happens due to the hydrogen bonding between the water molecules that we will talk about later on. But essentially what happens when you put a liquid in a graduated cylinder, a liquid like water that is, you're going to end up with this little this depression that you're going to see if you take a very close look, right? The water is going to bow down like this, and this depression here is called a meniscus. And when we take a reading from a graduated cylinder, we always want to measure from the bottom of the meniscus, so you need to get eye level with this meniscus here to take a reading. Okay, so it says right here, always take your measurements from the bottom of the meniscus. And when using a graduated cylinder to measure the volume of a liquid, you must first determine the degree to which your graduated cylinder is calibrated, like we just talked about. If we take a look, these two graduated cylinders are graduated by different increments. We can see right here that the increments right here are going to be 0.1 milliliters, whereas the increments right here, if we take a close look, are 0.2 milliliters. And so if we wanted to determine the volume of water that's in here, we can see that we have 4.1, 4.2, and this is right on the 4.3 line. So 4.3, but keep in mind that we need to go one significant figure beyond the level of precision, so this will end up being 4.30 milliliters. And if we take a look at this one right here, this is 16, 16.2, 16.4, 16.8, and then it's just a little bit past the 16.8, so we'll call this 16.81 milliliters. Alright, so let's go ahead and try some measurements of volume, and let's apply these concepts and see if you can get them right. So let's take a look at this first example. We have a graduated cylinder with some liquid in here, and we need to determine what the volume of the liquid is. So the very first thing that we need to do here is determine by what increments our graduated cylinder is graduated by. So if we take a close look, we can see that this is 1 milliliter here, and that this is going to be 2 milliliters right here. So we have 1 ml here, 2 mLs here. So it looks like each one of these little lines here represents 0.1 milliliters. And so now that we know how our graduated cylinder is graduated, what we can do is figure out the volume of the liquid that's in here. And if we take a close look, we can see that this is going to end up being, with 100% certainty, 5 milliliters. With 100% certainty, we know that it's 5.2 milliliters. And if we take a very close look, this blue dashed line is just a little bit past this 5.2 line, so we'll call this 5.21 milliliters. So the volume of the liquid in here is 5.21 mLs or milliliters. Let's take a look at another example. In this second example, first of all, we need to determine our the precision of our graduated cylinders. So if we take a look here, if this is 2 milliliters and this is 4 milliliters, then each one of these little lines here is going to represent 0.2 milliliters. So we have a cylinder here that's graduated by 0.2 milliliter increments, and now we have to determine the volume of the water that's in here. So if this is 12 milliliters, we know with 100% certainty that this liquid that is in this graduated cylinder is going to end up being 12.2, 12.4, 12.6, 12.8. It's going to 100% be at least 13 milliliters. So we know it's 13 milliliters with 100% certainty. And then if we take a closer look, it's 13.2 milliliters with 100% certainty. And if we take a closer look, this blue dashed line is just a little bit above the 0.2 line. So we'll end up with 13.21 milliliters. Now if you said this was 13.20, the teacher will probably find that to be acceptable. If you're within 0.01 milliliters when you're taking a reading from a graduated cylinder, you're not doing too bad. Let's take a look at another example. In this example, once again, we have a liquid that is in this graduated cylinder. We need to determine the precision of our graduated cylinder. So if we take a close look, this is 5 milliliters here, this is 10 milliliters. So what do each one of these little lines here represent this time? Well, if we take a look here, each one of these little lines is going to represent 0.5 milliliters. And so our graduated cylinder here is graduated by 0.5 milliliter increments. So to determine the volume of the liquid that's in here, we can see that we have 25 milliliters right here, 25.5 milliliters, 26 milliliters right here, 26.5 milliliters, 27 milliliters. So we know with 100% certainty that the volume of the liquid that is in here is going to be 27 milliliters. And now if we take a look, we can see it's not quite 27.5 milliliters, it's just a hair below that. So we'll call this 27.3 milliliters. So the volume of the liquid that is in this graduated cylinder is 27.3 milliliters. And you can see now why it is that when we have a graduated cylinder that is graduated by 0.5 milliliter increments, we can only take that measurement to the 10th place. We had to estimate the 10th place, and therefore you cannot estimate two significant figures in a measurement, only one. That is why this is 27.3 and not 27.30. All right, let's take a look at another example. So how can we use a graduated cylinder and water to determine the volume of an irregular shaped object like a screw? If we have an irregular shaped object like a screw, we don't have a mathematical formula that allows us to determine the volume of a screw or an irregular shaped object. So how can we figure out the volume of this screw? Well, we can use something called water displacement to determine the volume of this screw right here. And here's how it works. First, what we'll do is we're going to fill this graduated cylinder up with an arbitrary amount of water. It needs to be enough water to cover this screw right here. What we're then going to do is we're going to take an initial reading of the water that we placed in this graduated cylinder right here. Once we take that initial reading, or that initial volume, we're going to put the screw in here, and what's going to happen is that the water level is going to increase. What we're then going to do is we're going to take the final volume of the liquid that is in this graduated cylinder, and what we can end up doing is subtracting the two to get the volume of the screw. So if we take a close look here, we can see that the initial volume of the water that is in this graduated cylinder here is 22.3 milliliters, right? We're going to put the screw and the water level is going to rise, and the final volume now of the water that is in this graduated cylinder is 42.0 milliliters. And so to get the volume of the screw, it's simple. We take the final volume minus the initial volume, and when we do that, we're going to end up with 19.7 milliliters. Now it's important to keep in mind that a milliliter and a cubic centimeter are the same thing. It's the same exact measurement. We use centimeters cubed though for solid objects. So we can just go ahead and turn this milliliters into centimeters cubed. And so the volume of our screw here is 19.7 cubic centimeters, and the method that we use to determine this is something called water displacement. Okay, so we take the final volume minus the initial volume and we'll get the volume of our screw. So let's take a look at another example here. We have a rock here and we want to figure out the volume of a rock. Well, there is no formula that allows us to figure out the volume of a rock. So what we can do is we can use water displacement. So if we take a look, we can figure out the initial volume of the water that is in this graduated cylinder. We could then put the rock in here and we can figure out the final volume of the water level that is in this graduated cylinder. So let's go ahead and do that. If we take a look, the volume, the initial volume of the water that is in here is 12.19 milliliters. We're then going to put the rock in here, the water level is going to rise, and now the volume of the liquid that's in this graduated cylinder is 16.19 milliliters. So our final volume is 16.19 milliliters, our initial volume is 12.19 milliliters, and we take final minus initial volume to get the volume of our rock. And so the volume of our rock is going to be 4.00 milliliters, or 4.00 cubic centimeters. And so keep in mind the rules of significant figures. When we're adding and subtracting, we have 2 decimal places here, we have 2 decimal places here, so we must keep those decimal places in our answer. If you just put 4 cubic centimeters as a final answer, that would be incorrect. 4.00 cubic centimeters is the correct answer here. Okay, so keep in mind those rules of significant figures. So now that we know how to measure volume, let's now switch gears and figure out how we're going to measure temperature from a thermometer. So let's now take a look at how we're going to measure temperature. When we measure temperature from a thermometer, the rules are very similar to the rules that we learned about taking measurements of volume. It says right here that when taking a measurement from a scaled instrument such as a thermometer, you must record the measurement one significant figure beyond the level of precision of the instrument that you use to take the measurement. And so here are the different rules that you can pause and read. Let's go ahead and apply these to a couple different images of a thermometer. We have a thermometer here and we're asked to determine the temperature of this object that is represented by this thermometer here. The very first thing we're going to have to do is figure out how the thermometer is graduated by. And so if we take a look here, we can see that this is 0 and this is 10 up here. So each one of these little lines here represents 1 degree Celsius, right? So the thermometer here is, we can call graduated by 1 degree Celsius increments. Therefore, the reading of the temperature here is going to be 20, 21, 22, 23 with 100% certainty, and we're going to have to estimate one significant figure beyond the level of certainty. So if we take a look, it's graduated by increments of 1. We need to go 1 beyond that to the 10th place. And so we estimate that this is going to end up being 23.8 degrees Celsius. If we take a look at this thermometer here, we can see that this thermometer is graduated by increments of 5 or 5 Kelvin. If we take a look, this is a Kelvin thermometer, this is a Celsius thermometer. And so if we're asked to take the temperature here, we can see that this is 150, this is going to be 155, this is going to be 160, 165, and it's just a hair above 165. So we have to estimate what that's going to be, and we're going to call this 166 Kelvin. So the temperature here is 166 K. So let's go ahead and apply these concepts here to several different images of thermometers and see if you can determine what the temperatures are. And so it says to measure the temperatures indicated on the thermometers below. So we have 4 thermometers here. First of all, we can see that these thermometers are measuring in degrees Celsius. And then we need to take a look at how they are graduated by. We can see that all of these thermometers, they appear to be graduated by 1 degree Celsius increments, right? So all these are increments of 1 degree Celsius. So if we're asked to determine what the temperature here is, we can see 0 is here. And so if we count backwards from 0, this is -1, -2, -3, -4, -5. Here's -10, here's -11, here's -12, and it's just beyond -12. So we're going to estimate this to be -12.4 degrees Celsius right here. So the temperature on this thermometer is reading -12.4 degrees Celsius. Let's take a look at this one. We have 10 degrees Celsius, and if we take a look, the blue dashed line is exactly on the 11 degree mark. So if we just put 11 degrees Celsius, this is going to be incorrect. Remember, we have to measure one significant figure beyond the level of precision here. This is precise to the ones place, so we need to go 1 decimal further. So we have to add the 0 here. So the temperature on this thermometer reads 11.0 degrees Celsius. Let's take a look at this example right here. We have -10 degrees. It's not quite a -11, so we'll call this -10, -10.5 degrees Celsius on this thermometer here. And if we take a look at this one here, here is 0. Here is 5 degrees Celsius, so here is 4, and it looks a little less than halfway between these two lines, so we'll call this 4.4 degrees Celsius. So that is how we're going to take measurements of length, volume, mass, and temperature. And if you like what you see, go ahead and click that little bomb in the bottom right hand corner, and that will subscribe you to my channel. And feel free to leave any comments or questions in the comment section down below. And I really hope you guys found this helpful.